Hello, my name is Justin Gonzalez, and this is my partner,
Ruben Topete.
and this is our research project on differential equations in electrical and energy engineering.
What are these areas? So, energy engineering focuses on developing and implementing technologies to ensure that energy is produced, used, and managed in a way that supports economic growth and environmental sustainability. I'm interested in energy engineering because it addresses some of the biggest challenges we face today and the possible problems we may face in the future.
For electrical engineering, specifically power and energy, they design and analyze electricity, electronics, circuits, power generators, etc. They ensure distribution of power is flowing smoothly and efficiently and safely. I'm interested in electrical engineering because it is the future and it's something I want to be a part of. Ever since I was younger, I always was fascinated by electricity and the way electronics and devices worked. Applications of differential equations in our major. Differential equation is an essential part and often used in electrical engineering and energy engineering. Let, for electrical engineering, I chose the application of first order linear differential equations. My partner Ruben chose the Laplace transformation for energy engineering.
How do they do this? The Laplace transform is an essential tool for energy engineers because it simplifies the process of solving complex differential equations. By transforming these equations into a more manageable algebraic form, the Laplace transform reduces both the complexity and time required to find solutions. Without it, engineers would have to rely on more complicated methods, making the problem solving process much more challenging and time consuming.
For electrical engineering, the application of first order linear equations is used to calculate electrical quantities change over time. These systems, when shut off or turned on, don't immediately shoot up or down. They rise or fall exponentially. Talking a little more about my major, electrical engineering, using the first order linear differential equation is so important because they help understand the control of power, transfer, safety, stabilize power systems. Without this, we wouldn't be able to predict how fast current rises and how much power is entering the circuits, etc. Thus, it would also be very dangerous. With first order, we see how the system is moving and distributing itself. RL circuits first order linear equations. When going through this research from the article, I realized that the equation is similar to what we learned in class in 1.5. I thought that was really cool and how they are the same idea, just different context. This equation is used to design and understand systems that deal with rapid or high changing currents. The variables that are listed represent different things. For instance, Vt is the voltage with respect to time. I is the current in the circuit in to respect to time. L is inductance. R is the resistance. This equation is heavily relied on all across electrical engineering since it shows us how voltage and current interact in real circuits and real devices, which make it important because without this, many of the devices would become non operational. The importances of RL circuit first order linear equation. The RL circuit is tasked with doing is describing the current changes over time when voltage is present. It controls how current flows, ensuring they can deal with high or rapid changing currents. This is used in many devices such as transformers and power systems. As we see in the picture to the left, The power station is where energy is generated and sent to a power transformer. The transformer would then regulate the voltage and current so it doesn't overload and become too much for the grid to handle. If the vol- if the current and voltage become too much, the system will overload and become non-operational. That's where these circuits come in. They ensure that energy is flowing through the system properly and regulated for a smooth distribution to the city or town. Therefore, this equation is really important because it helps engineers predict and manage how current is flowing every day and making sure it is stable. Before moving on, I want to highlight a time constant for RL circuit. It's going to be the equation to your left, T equals L over R. It highlights how fast current rises when the circuit is on and how fast it will fall when it's off. It tells us the system how it's going to behave when it's switching or surges. T equals, as stated from the article, is a time constant that describes the duration of transient. The first order differential equations in RC circuits. This is represented as the key equation to the left. Some of these variables represent different things. For instance, Qt is the charge on the capacitor in respect to time. The derivative of Qt is the change of rate in the current into the capacitor. R is the resistance in the circuit. C is the capacitance. Vt is the voltage with respect to time. R, RC to the opposite power is the inverse of time constant. The 1 over R Vt is how much voltage affects the change of rate of charge. The importance of first order differential equations in RC circuits. RC circuits are described as voltage and charge change over time. The capacitor will store energy and resist sudden changes in voltages. They're important in filtering, timing, and making the voltage run smoothly in every device. A great example of this would be phone chargers, as phone chargers reduce the amount of voltages traveling to the phone. A normal household will have an average of 12 voltages, while a phone will only be able to take 5. So the charger will reduce the amount of voltages going into the phone so it doesn't stress itself and eventually damage the phone.
Energy engineering. The Laplace transform helps engineers by turning complex problems, often described by time based equations, into something easier to handle. This powerful tool effectively transforms difficult calculus operations like differentiation and integration into straightforward algebraic equations within the intermediate S domain. The main advantage is that problems become significantly simpler to solve algebraically in this domain, making the solution process much more efficient. Once the solution is found in the S domain, engineers use the inverse Laplace transform to convert it back to time domain, which gives us real world time based answers. Lightning strikes, wind turbines, and Laplace transforms. One of the major challenges energy engineers face is the impact of lightning strikes on electrical infrastructure. Lightning is fast, high frequency, and unpredictable. When it strikes power lines, transformers, or renewable energy equipment, it can cause severe damage, unexpected shutdowns, and long term degradation that may not be immediately visible. For instance, wind turbines in storm heavy regions often experience hidden degradation. This refers to internal damage or weakened insulation that builds up over time after repeated lightning strikes. While the damage might not be visible from the outside, it can lead to decreased performance, increased safety risk, higher insurance and maintenance costs, and more downtime. The problem becomes even more complex because lightning strikes happen in extremely short time frames, often in microseconds. This makes time domain math very challenging, and the differential equations that model these events can be nearly impossible to solve directly. This is where the Laplace transform becomes useful, as it helps to simplify these complex problems into more reasonable equations. Laplace transform in lightning current analysis. In one study, the researchers applied the Laplace transform to handle lightning measurements. Lightning strikes happen in microseconds and they're very high frequency, which makes solving the equations in the time domain very challenging. By using the Laplace transform, they could account for time delays in the measurements. They did this with a simple multiplication in the S domain, then used the inverse transform to reconstruct the base current waveform. This first equation shows how the time shift in the lightning current is represented in the Laplace domain. In reality, the lightning current doesn't instantaneously affect the measurement point. There's a time delay, delta t, because the electromagnetic wave from the lightning travels at a finite speed. In the Laplace domain, this time delay is represented by multiplying by e to the minus s delta t, which lets engineers account for it without having to deal with complex time-based integrals. The second equation is the inverse Laplace transform. Once we have the function IBS, the S-domain version of the lightning current, this formula converts it back to the time domain, giving us the real-time waveform we need to analyze, design, and protect systems. In this equations, we have IBT, which is the time domain function, IBS, which is the S domain function, delta t, which is time delay constant, I, which is current, B, which is base, e to the power of negative st, which is the weighting factor, s, which is a complex frequency, t, which is time, L, the Laplace transform, and L to the negative 1 power is the inverse Laplace. Laplace transform in surge energy distribution. Another area where Laplace transforms are extremely useful is in surge energy distribution, which deals with how electrical surges travel through power networks. Energy engineers design systems like substations, renewable energy inverters, and industrial power supplies, all of which must be able to withstand sudden spikes caused by lightning or switching operations. Surges can stress equipment far beyond its normal operating limits, so engineers need to know how a surge moves, how much energy it carries, and how fast protective devices react. However, these surges occur so quickly that analyzing them directly in the time domain is extremely challenging. The Laplace transform again becomes a powerful tool because it simplifies these fast, high-frequency events into solvable algebraic equations. When engineers switch to the S domain, they gain the ability to track where energy is flowing during a surge, how a waveform evolves along a transmission line, and how protective components like surge arresters or filters respond to these changes. This helps them optimize protection strategies, prevent equipment failure, and design more reliable power distribution systems that can safely handle extreme events. The first equation is written in the time domain. It's an integral differential equation, meaning it contains derivatives and integrals, which makes it difficult to solve directly, especially during fast surge events. When we apply the Laplace transform, we get the second equation. All the derivatives and integrals turn into simple algebraic terms. In these equations, we have V at t, the time domain voltage function, I at t, the time domain current function, R, which is resistance, L, inductance, C, capacitance, V s, voltage function in the S domain, Is, current function in the S domain. Connection. Both electrical and energy engineering overlap in several major areas. Electrical engineers provide the core technologies like generators, inverters, and power electronics, while energy engineers focus on how these systems produce, store, and use energy efficiently. Together, they work on renewable energy integration, grid stability, and energy efficiency. In short, electrical engineering builds the hardware, and energy engineer optimizes how that energy is managed.
And this right here will be our sources that we use throughout the video. Thank you for watching.